the Feynman Lectures on the Character of Physical Law. You are listening to Brothers of the Serpent podcast.
And welcome back, ladies and gentlemen, boys and girls, angels and demons and monsters and serpents. This is Brothers of the Serpent podcast, and we are coming to you not live from the 10 by 10 by 10 tangent cube of science, where we are nestled amongst the dusty bones of an ancient seabed high atop the Edwards Plateau. And Kyle's still climbing around the studio, setting stuff up.
Everything was rearranged for the rock and roll interview.
Yeah, which will be dropping on the solstice. We did a special sort of bonus special episode of where we interviewed the $50 Dynasty Band, most of it. The drummer wasn't here, but yeah, we're going to be gone to Montana during this period, during the solstice period, or like right at the end there. And so that interview will probably drop with the album at the same time, roughly. So you guys can look forward to that. It was a fun interview. And it's also available right now on the $50 Dynasty Patreon if you want to hear it now.
That's right. And the Patreon's doing great. Much appreciation to everybody who's supporting the band.
Yes.
That's been
much appreciation to everyone who supports the show and the band.
Yeah, there's lots of doubles in there.
Yeah, there's some crossover. Yeah.
Really appreciate it, guys.
What else we have? We have any we got ag updates.
Did we talk about the thin fruit? I don't think I did.
No, we didn't.
So yeah, we had to drop a bunch of fruit on the hillside vineyard. We have 3 acres on the side of a hill. They're in their second season of growth, and they put on a lot of fruit.
Yeah.
So the idea is to cut off most of that fruit so that the vine can use the energy that it has and gains throughout the season to build more vine and grow a bigger root.
Stronger trunk, stronger roots. Yeah.
And so we left, a couple of clusters on some vines. A few vines had maybe 4 or 5 clusters because they were already big and lush. Some of them that were pretty small were just loaded down with fruit, and we just dropped all the fruit off. So yeah, it's like a balancing act. You don't want to cut too much off because then they may, go crazy.
Yeah.
You
want them to have a little bit of fruit stress, but
you want to slow them down a little bit. Yeah. So
we keep talking about like, well, maybe we'll harvest a ton or 2 tons off the hill, but no, we're just feeding the birds.
Yeah, probably gonna feed the birds. Hey, Ty told me about a method where you get these really tall poles. They put these real tall poles out in the vineyard, so like 20 feet, 20-foot pole. And at the top is a string with a hawk kite.
Oh.
And it just blows around. And this hawk is like, so you can put a bunch of them up in the vineyard and the birds don't go anywhere near it.
Hey, that's a great idea.
I'm like, yes, I got to look these things up.
Yeah.
Thanks for the pro tip there, Ty. How did this happen?
Because he's working at Slate Mill or Slate Theory, yeah.
Yeah, so we got to try it.
Yeah.
The other option is to net.
No, we don't have the nets for that yet.
We have some, but not enough. So yeah, we've basically got everything kind of pruned. We've putting the catch wires up to hold the shoots vertically. The whole vineyard just looks amazing right now. No rain. We've been watering a lot, and I'm gonna have to be putting on like a gallon a day. So it's we'll do 8 hours this week or something of water.
Yeah.
Across the whole vineyard, it takes
a long time.
A while. Yeah.
Yep. And people should know that in case we haven't mentioned this before, and I need to put this up on the website, but you can order the wine. It is available if you just go to the website. What's the website for the tasting room?
It's Turtle Creek Olives and
Vines.com. Right?
Yeah.
So if you just go to turtlecreekolivesandvines.com, you can find either just a way to contact them directly, like find the phone number and call them, or there's probably a way there to just order the wine you want. Make sure it's one of the Turtle Creek vintages because they do offer lots of different stuff. But if you want to try the wine we've made, You can find it on the website there, and it's now available to order at least all in the lower 48, I think, right? Do they ship to Alaska?
There's some states we can't ship to.
Right.
And it's not just the 48. It's some of those I think we can't ship just because of those state laws.
Okay, the laws,
Like they're protecting their own viticultural area, or I don't know if it's a their wine industry by saying no out of state shipping.
So no, not globally, and not all of the states, but some of them. So if you want to try our wine, you can check out on the website to see if you can get some if you're in the States.
And the stuff
I don't know if we'll ever be able to like ship to Australia.
The black labels, the black label wines are all our own fruit that we grew and we made the wine.
Yeah.
So there's white label Turtle Creek wines and the white label, or they're kind of ivory. We just call them the white labels, but they're we're making the wine, it's like we're buying bulk wines from other Texas wineries and blending or some function like that. So it wasn't all made by us, and it is not all our fruit.
Yeah. Yeah, so if you want to specifically try the stuff that we grew and then we made in our winery, it's the black label you want.
Yeah.
All right, there's your agricultural update for the week. All right, let's go ahead and do space for the news.
Roll update.
Oh yeah, you got the rock and roll.
I don't. It's for some reason it won't stay in the sampler.
Oh,
why I have to like reload it every time? It's crap. Let me see if I can do it here. Here we go.
Excellent.
Oh, there it is. There you go. All right, let's do space for the news, if we can.
Okay. Yeah.
From spaceweather.com, where we always get all our space weather news. CME near miss possible on June 5th. A minor coronal mass ejection that left the sun on June 1st will pass close to Earth on June 5th. According to NOAA analysts, it might come close enough for a glancing blow, so high-latitude sky watchers should be alert for auroras when the CME arrives this weekend. Also, a daytime meteor shower is underway. One of the strongest meteor showers of the year is underway, but you might not notice because of the glare of the sun. The Canadian Meteor Orbit Radar is picking up significant activity less than 20 degrees from the sun. In the radar map, the radar sky map, ARI stands for, Aerated Meteor Shower. Its source is the sun-grazing comet 96P, which has laid down a trail of debris in the early June portion of Earth's orbit. When the shower peaks on June 7th, CMOR will detect approximately one meteor every 20 seconds, a rate which ranks these aeratids among the top meteor showers of the year. So it turns out that June is the best month of the year for daytime meteor showers. When these subside, another daytime shower will take over. The Zeta Perseids peak on June 13th, and then another, the Beta Taurids, on June 29th. If only we could see them. That's what they say at Space for the News. Current conditions. Solar wind speed is 279.3 kilometers per second. The density is a very high, 13.79 protons per cubic centimeter. I just wonder, like, I wonder if we could find a ratio between these. Like, the speed when it's high, the density is low.
Yeah.
The density's high when the speed is
you're
low.
Getting all into the mathematics, man. You're trying to find some kind of connection.
There's got to be a connection here. The sunspot number right now is 75.
Wow.
The neutron count is 4.7% above the space age average, which is one of the lowest readings I've seen since we've started doing this. And the KP index right now is 1, which is quiet. 24-hour max also 1 at quiet. There's your space weather news for the week.
Cool.
Crypto, Bitcoin. Where's my bell? Bitcoin is $31,297.81, and Ethereum is $1,857.61.
It's going up.
It is. Well, it looks like Ethereum is down, but Bitcoin is up for sure.
All right. Thanks for that update.
Mm-hmm.
I pulled this story just for you, bro. This is from earthsky.com. A sharkcano.
Yes.
An undersea volcano where sharks live. This story was making the rounds on social media on May 25th, 2022. Researchers have dubbed the underwater Cavaci volcano a sharkcano after finding sharks living in its submerged crater. The Cavaci sharkcano lies in the waters off the Solomon Islands in the ocean near Australia and Papua New Guinea. Cavaci began an eruptive phase in October 2021, and satellite data showed discolored water around Cavaci on several days in April and May 2022, indicating eruptive activity. NASA Earth Observatory shared the satellite image showing discolored waters rising upward from Cavaci on May 14th. The last large eruptions at Cavaci occurred in 2014 and 2007, though the volcano erupts nearly continuously. Nearby residents often report seeing steam and ash. Scientists found 2 species of sharks, including hammerheads, living in the submerged crater during a scientific expedition to Cavaci in 2015. Submarine plumes of superheated acidic water, such as the one from Cavaci, usually contain particulate matter, volcanic rock fragments, and sulfur. The scientists also found microbial communities thriving on the sulfur. The Landsat 9 satellite took images of activity from the submarine volcano. In the images, you can see the volcano emitting a plume of discolored water. From the wider view image below, which you guys can't see, you can see that Cavaci lies 15 miles south of Vangunu Island. The region around the Solomon Islands is an active area near the subduction zone where 2 plates come together. What I really want to know as I'm going through this story is, did it throw the sharks into the stratosphere?
Yeah.
And they're not telling me about this.
And then you have the Sharknado.
That's what I'm talking about.
Yeah.
This is some Fortean possibilities here.
Yes.
So, and then they talk about the island. Come on, tell me what's the deal. Bottom line, here we go. The underwater Cavaci volcano in the Solomon Islands is being called a sharkcano because scientists found sharks living in it. Dang it.
It's not what you want, huh?
That's not what I wanted.
Yeah, that's good.
Just Sharknadoes and Sharkanos.
Yes.
Oh, man. I've got some other cool stories here. A little bit on the lost Amazonian civilization, perhaps?
Yeah.
Okay. From ancientorigins.com. This is updated the 26th of May, 2022. LiDAR identifies vast complexes of a lost Amazonian civilization in Bolivia. Researchers in northern Bolivia have used LiDAR to identify a series of raised platforms and pyramids, interwoven by a complex hydrological network. These abandoned sacred sites are relics from a lost Amazonian civilization. The Casarabe people, pop-ups, inhabited what is widely regarded as the most fertile farming land in the Llanos de Mojos region of northern Bolivia in the Amazon basin. Or I guess it might be Llanos, L-L.
Yeah.
A-N-O-S, Llanos de Mojos. Anyway,
Well, I think when it's 2 L's at the beginning, you do like
Llanos?
llama, right?
Okay.
I don't know. Don't ask me.
Yeah, all right. We don't know. Between 500 and 1400 AD, farmers in this lowland tropical savanna built a complex network of cities and towns amidst almost 1,000 kilometers of canals and mud causeways.
Wow.
500 and 1400 AD. So this is like contemporary with the Pueblo,
Yeah.
like building the cliff dwellings and all that kind of
Well,
stuff.
wasn't that 1100 AD? Or was
I
that
think
when
it was
they collapsed?
between 600 and 1100 AD.
Okay. Yeah, they collapsed at 1100 AD. Maybe is what
Yeah.
it was. Yeah.
They seem to vanish
Yeah.
around 1100, and it sort of starts at 600-ish.
Okay.
I think that's... Anyway, farmers in this lowland tropical savanna built a complex network of cities and towns amidst almost 1,000 kilometers of canals and mud causeways. Now, scientists flying LiDAR scanners have revealed evidence of hitherto undiscovered settlements built by a lost pre-Hispanic civilization. Oh. Ars Technica explains that history has forgotten what these people called themselves, So the Kasarabe people are named after the nearby colonial town. A new study published in the journal Nature claims to resolve a long-standing scientific debate about whether this region could have sustained a large population in ancient times or not. Previous surveys in the Llanos de Mojos identified hundreds of mounds. Most of these were concentrated within a 4,500 square kilometer section of plains around the modern Bolivian towns of Casarabe. However, 16th century Spanish missionaries only recorded finding small, isolated communities of farmers living in the region. So, 16th century, so we're talking about 1500s.
Yeah.
So all they have, they're finding small, isolated communities in the 1500s, and they're saying that these people that built all these pyramids and miles of aquifers and canals and vanished in 100 years before that. And now there's just tiny communities. I don't know. Study lead author Heiko Prumers, an archaeologist at the German Archaeological Institute in Bonn, told Live Science that scientists in the 1960s interpreted these earthen mounds as ruins or natural features. Penetrating the dense Amazonian vegetation with airborne LiDAR, the team of researchers have successfully identified the nature of several unknown mounds in areas now known as Kotoka and Landivar. They turned out to not be natural piles of dirt, but vast ceremonial centers with huge raised platforms of earth topped by enormous pyramids, according to the study. The new paper describes two large Kasarabe settlements that stood central in a network of roads, causeways, reservoirs, and canals. Contrary to Spanish accounts, according to Prumers, this region was very densely populated in pre-Hispanic times. The archaeology, it turns out, is so thick in this region that earlier scientists thought the proliferation of mounds must have been geological. Prumers concluded that Kasarabe people had instituted a low-density tropical urbanism across a vast area.
This kind of reminds me of the... I'm not going to be able to remember the specifics of the names here, but there was a guy, an early Spanish explorer who traveled the Amazon River by boat, and I can't remember exactly the details, but it was something like he wanted to go a specific distance and come back, but he couldn't. So he ended up going along a large percentage of the river itself, just because he had to just keep going downriver. And in his report, he reported enormous communities with, advanced constructions, big cities, all this kind of stuff. But then, 100 years later, when people went to these regions again, they didn't find anything.
Yeah, right.
And so they all thought he was full of crap, and how could this, so there is some evidence.
I guess if you had...
There is some evidence that there was an enormous population collapse.
Right, if there was something, then everybody got sick and died.
Yeah.
100 years later, there'd be no trace.
The jungle's going to just be, yeah.
I mean, think of it, 100-year-old tree.
Yeah.
If you're not cutting back the weeds, man, it's going to go crazy.
Yep.
Okay, moving on. Let's see. Prumers, the archaeologist, said that 24 butt flap ceremonial sites have now been identified in the area. No less than 9 of these were found for the first time in this latest LiDAR study. While the 2 major sites at Kotoka and Landivar were known about previously, their true extent has only now been revealed by LiDAR, said Prumers. It was revealed that these 2 mega settlements were joined by a complex matrix of roads and causeways forming loose concentric circles. Extensive waterways radiated out in all directions from the 2 major settlements, which the researchers said represented a major investment in landscape management and labor mobilization. Think about this. Concentric circles containing water.
Yeah.
Prumers said this complex hydrological system perhaps controlled seasonal floods and enabled the farming of maize and other crops in higher areas, while fish might have been farmed in lower flooded parts of the landscape. Maybe it sank into a sea of trees. The researchers also determined that the ritualistic platforms and ceremonial pyramids. God, this is so annoying. Were like, okay, we just found these things that we completely understand what they were used for.
Yeah.
And we are okay. So
and we're calling it's clear that it's irrigation and maybe have possibilities for farming
just ceremonial
but they're totally ceremonial and ritualistic.
Right. The raised platforms. So yeah, the ritualistic platforms and ceremonial pyramids were oriented facing the northwest, the northwest. The scientists said this was the same direction as most of the Kasarabe burials that have been found. So they're burying their people in the same orientation. I'm assuming that's what he means by burials.
Yeah.
This predominant astronomical alignment, along with the ceremonial pyramid structure, they can't say pyramid without saying ceremonial. Along with the ceremonial pyramid structures, suggests a well-developed cosmovision or community-wide religious beliefs. Because, when you're looking at the stars, it's religious.
It's definitely religious. Yeah.
Whatever spiritual practices may have gone on here certainly didn't work. For the study concludes, water scarcity brought about the demise of the Kasarabe civilization around 1400 AD, and we are a bunch of arrogant assholes. This collapse occurred more than a century before the Spanish conquistadors arrived. Thus, the pyramids erected in the honor of ancient sky gods, it would seem, had lost their lifeblood through droughts a long time before the dragons arrived to scorch their land.
Wow.
Now, I have to say, ceremonial sites is quoted by Prumers, who's the German archaeologist, one time. I believe that most of these other, in the story at least, let's see. Yeah, so in other words, it could be the journalist.
Yeah, the author for Ancient Origins there.
Yeah.
Using that.
Yeah.
Yeah. So he quotes the archaeologist saying it.
I'm not saying that he didn't get it from the archaeologist.
Yeah.
But it's just, who knows? Mm-hmm. This is written by a journalist. The archaeologist is quoted as saying ceremonial pyramids one time.
Yeah.
So I don't know. It's awesome. It's so annoying that this is still the mindset going into looking at this, that we keep finding out that we're wrong.
Yeah.
There's more and more people. They were more and more advanced. Their civilizations go further and further back. And yet we still know what they were doing and why. And and now we mock them for their fake gods not working out.
Yeah.
It's just, okay. Sorry. I took that in a negative direction, but anyway, cool story. So,
yeah.
Should I do another? What else do I got? Got one about Mars. This is pretty cool. This is from phys.org. Great site.
Yep.
One of my favorite scriptard sites. Mars once ran red with rivers. The telltale tracks of past rivers, streams, and lakes are visible today all over the planet. But about 3 billion years ago, they all dried up, and no one knows why. People have put forward different ideas, but we're not sure what caused the climate to change so dramatically, said University of Chicago geophysical scientist Edwin Kite. We'd really like to understand, especially because it's the only planet we definitely know changed from habitable to uninhabitable. Kite is the first author of a new study that examines the tracks of Martian rivers to see what they can reveal about the history of the planet's water and atmosphere. Previously,
I feel like that guy should have studied gliders.
What are gliders?
Like aerodynamics.
Oh, yeah,
gliders.
Mr. Kite?
Yeah.
Yeah.
He's in the wrong profession.
Yeah. Previously, many scientists had assumed that losing carbon dioxide from the atmosphere, which helped to keep Mars warm, caused the trouble. But the new findings published in May 25th in Science Advances suggest that the change was caused by the loss of some other important ingredient that maintained the planet warm enough for running water. but we still don't know what it is. So they thought it was CO2, and then they were like, wait a minute, it's got to be something else. They don't know what. In 1972, scientists were astonished to see pictures from NASA's Mariner 9 mission as it circled Mars from the orbit. The photos revealed a landscape full of riverbeds, evidence that the planet once had plenty of liquid water, even though it's dry as a bone today. Since Mars doesn't have tectonic plates to shift and bury the rock over time, ancient river tracks still lie on the surface like evidence abandoned in a hurry. This allowed Kite and his collaborators, including University of Chicago graduate student Bowen Fan, as well as, we got Fan and Kite. These guys definitely make a good team. As well as scientists from the Smithsonian Institution, where everything vanishes. Planetary Science Institute, California Institute of Technology, Jet Propulsion Laboratory, and Aeolus Research analyzed maps based on thousands of pictures taken from orbit by satellites. Based on which tracks overlap which and how weathered they are, the team pieced together a timeline of how river activity changed in elevation and latitude over billions of years. This is obviously very gradualistic. Then they could combine that with simulations of different climate conditions and see which matched best. Planetary climates are enormously complex, with many, many variables to account for, especially if you want to keep your planet in the Goldilocks zone, where it's actually warm enough for water to be liquid, but not so hot that it boils. Heat can come from a planet's sun, but it has to be near enough to receive radiation, but not so near that the radiation strips away the atmosphere. Greenhouse gases, such as carbon dioxide and methane, can trap heat near a planet's surface. Water itself plays a role, too. It can exist as clouds in the atmosphere or as snow and ice on the surface. Snow caps tend to act as a mirror to reflect away sunlight back into space, but clouds can either trap or reflect light away, depending on their height and composition. Kite and his collaborators ran many different combinations of these factors in their simulations, looking for conditions that could cause the planet to be warm enough for at least some liquid water to exist in rivers for more than 1 billion years, but then abruptly lose it. But as they compared different simulations, they saw something surprising. Changing the amount of carbon dioxide in the atmosphere didn't change the outcome. That is, the driving force of the change didn't seem to be CO2. Carbon dioxide is a strong greenhouse gas, so it really was the leading candidate to explain the drying out of Mars, said Kite, an expert on the climates of other worlds. But these results suggest it's not so simple. There are several alternative options. The new evidence fits nicely with a scenario suggesting in a 2021 study from Kite, where a layer of thin, icy clouds high in Mars's atmosphere acts like a translucent greenhouse gas, trapping heat. Other scientists have suggested that if hydrogen was released from the planet's interior, it could have interacted with carbon dioxide in the atmosphere to absorb infrared light and warm the planet. We don't know what this factor is, but we need a lot of it to have existed to explain these results, Kite said. There are a number of ways to try to narrow down the possible factors. The team suggests several possible tests for NASA's Perseverance rover to perform that could reveal clues. Kite and colleagues Sasha Warren are also part of the science team that will be directing NASA's Curiosity Mars rover to search for clues about why Mars dried out. They hope that these efforts, as well as measurements of the Perseverance, can provide additional clues to the puzzle. On Earth, many forces have combined to keep the conditions remarkably stable for millions of years, but other planets may not be so lucky. One of the many questions scientists have had about other planets is exactly how lucky we are. That is, how often this confluence occurs in the universe. Strangely written. They hope that studying what happened to other planets, such as Mars, can yield clues about planetary climates and how many other planets out there might be habitable. It is really striking that we have this puzzle right next door, and yet we're still not sure how to explain it, said Kite.
Yeah.
Well,
I felt like there was like stacks of assumptions.
Absolutely.
In that. Yeah.
I mean, yes. At least
it's cool, but it's
at
like,
least they kicked out the CO2 model.
Yeah. It's cool, but it's like, well, we got this big stack of assumptions that says we need to figure out how the water was there for 1 billion years.
Exactly. That's what I'm saying.
Like,
this
you've
is
already got a
very
stack.
gradualist.
Yeah. And we've
But what
we've
can you
looked
do?
at some of those riverbeds with Randall,
Yeah.
and some of them are just like they have zero erosion around them, like that they flowed catastrophically for a brief period, and then they were gone, and there was no other water to
Right.
create the standard erosion features
Normally-
you see around any other riverbed on Earth.
Normally, if you have this giant channel, on the sides of the channel are fissures and
Yeah.
ravines and stuff from water running off the upper, like the what is it called? The uplands or the sub uplands
Yeah.
running into the river basin. So it's
Yeah, but these channels on Mars are just like pristine.
Yeah.
It's just one cut of a bunch of water, and then it all stops. There's
Yeah.
no secondary or, later erosion.
And it's also really cool because craters are preserved, and there's craters that are eroded by these giant channels. So
Yeah.
huge craters eroded by the channels, and then there's craters on top of the
On top of
channels.
the
and
channels,
it's-
yeah.
yeah. So
yeah,
there's
so
some
it
areas
implies
where
that there's just like a period of enormous amounts of water, and then it's gone.
right. Very cool stuff.
Yeah.
Check it out. Google Mars. Right?
Yep.
Yeah.
Mars. Okay, well, we're at the end of the segment, so let's briefly say what we're going to do here. We're going to tackle the character of physical law. This is a book that is basically a series of lectures by Richard Feynman.
You can find these lectures on YouTube.
Yep.
The
We'll have
character of
clips
physical
from that.
law. There is also an audiobook.
Yeah, on Audible.
Yeah.
Yeah.
Check it out.
Yeah, so stay tuned for that. In the second segment, we'll start The Character of Physical Law by Dr. Richard Feynman.
The artist of the Renaissance said that man's main concern should be for man. And yet, there are some other things of interest in the world. Even the artists appreciate sunsets and the ocean waves, the march of the stars across the heavens. And there is some reason then to talk of other things sometime.
And we're back, ladies and gentlemen, Brothers of the Serpent podcast. That was Dr. Richard Feynman that you were hearing there, giving his first lecture of Character of Physical Law.
That first lecture is the one we're tackling today.
Yes.
This book is fantastic. It's gonna be. I feel like so. Let's talk about this a little bit. We love doing physics on the show. Sometimes the physics is difficult to follow. So it's always kind of a balancing act, like how much do you go into the details and the math versus how much do you just try to describe it. And in the past, we've stuck to the descriptions, But one of the things Feynman is tackling in this series of lectures is that at least you need a little bit of the understanding of the math to see connections between things and then how we can progress through physics. And like once we'll get into this, but it's interesting how he's trying to give a series of lectures to a large audience of people who aren't all physicists and mathematicians.
They're like freshmen coming in.
Yeah.
And not all of them are going into the math department or going into the physics department. They're just
Right.
It was basically like, we're inviting you to come, and the idea was to give them some idea of like what's going on here.
Right.
And maybe inspire some of them to join the
Change
effort.
their major.
Yes,
Yeah.
exactly.
Right. Right.
And so he is speaking to the layman.
Yeah.
And that's
To
what-
us.
Yeah, he's speaking to us.
Yeah.
And so it's wonderful. I love this book so much.
Yes, the book is great. And of course, all of these are, like Kyle said earlier, all of these are available on YouTube. You can watch the full lectures. There's 7 of them. The book is divided into 7 chapters, 1 chapter per lecture. Today, we're going to tackle the first lecture, which is called The Law of Gravitation, an example of physical law. It has so much stuff in here that we've talked about previously on the show in different ways, but Feynman is, of course, tackling it in his very specific and awesome way. And Kyle's taken clips from this lecture, so we'll intersperse our discussion with clips, plus me reading from the book. So this is going to be an interesting, attempt, a new way of doing this kind of book report. because it's a book report, but it's also a report on a series of lectures that you can watch. So we do encourage you to go and check out these lectures because there's diagrams, and he's drawing all over the chalkboard as he's walking around on this stage. So continuing on with what Feynman was saying there, he says, as we look into these things, we get an aesthetic pleasure from them directly on observation. There is also a rhythm and a pattern between the phenomena of nature, which is not apparent to the eye, but only to the eye of analysis. And it is these rhythms and patterns which we call physical laws. So what I want to discuss in this series of lectures is the general characteristic of these physical laws. That is another level, if you will, of higher generality over the laws themselves. Really, what I am considering is nature as seen as a result of detailed analysis, but mainly I wish to speak about only the most overall general qualities of nature. So in this first lecture, I'm going to try to give, instead of only the generalities, an example of physical law, so that you have at least one example of the things about which I am speaking generally. It's interesting how he uses these, the specific, special, and general, in the same way that, you have special relativity and general relativity, meaning the more general it gets, the more it applies broadly across the entire, numerous systems, whereas special is it applies in this one case.
Right.
And so the more, that's what he's saying when he's saying general here. So he says, I have chosen for my special example of physical law the theory of gravitation, or the phenomena of gravity. So this law has been called the greatest generalization achieved by the human mind. And you can guess already from my introduction that I am interested not so much in the human mind as in the marvel of a nature which can obey such an elegant and simple law as this law of gravitation. Therefore, our main concentration will not be on how clever we are to have found it all out, but on how clever nature is to pay attention to it. The law of gravitation is that two bodies exert a force upon each other, which varies inversely as the square of the distance between them, and varies directly as the product of their masses. So mathematically, we can write that great law down in the formula, and he has the formula here, F equals G times the two masses divided by the square of the distance. G being the constant of gravitational constant. Mm-hmm. So he says, this is some kind of constant multiplied by the product of the two masses. Now, if I add the remark that a body reacts to a force by accelerating or by changing its velocity to an extent inversely as its mass, or that it changes its velocity more if the mass is lower inversely as the mass, then I have said everything about the law of gravitation that needs to be said. Everything else is a mathematical consequence of those two things. Now, I know that you are not all mathematicians, and you cannot immediately see all of the consequences of these two remarks. So what I would like to do here is tell you briefly of the story of the discovery, and what some of the consequences are, and what effect this discovery had on the history of science, and what kind of mysteries such a law entails, and then something about the refinements made by Einstein and possibly the relation to the other laws of physics. So this is cool. One of the things we love to do on this podcast is the history of discovery.
Yeah.
So we did this with Egypt extensively and in other places, and now we're doing this with physics with Feynman. And it's really great how he just details the history of the discovery of this, and he's right. The way you can see how, as you're going through this, how it informs all of science, or at least all of physics and cosmology and the hard sciences.
But it at the same time of being an example, a special example of, just like a phenomenon of physics or a physical law, it's a special example of how to do science at the same time, which is what everything else ended up utilizing these same principles.
That's what I mean. Yeah.
Yeah.
That this history of discovery, he mentions in here about, he's like, why am I not telling you about something more recent? And he's like, well, the reason I want to tell you about this one is because it also informs you about how we've learned how to do science.
Right.
Right. So he says, the history of the thing briefly is this. The ancients first observed the way the planets seemed to move in the sky and concluded that they all, along with the Earth, went around the sun. This discovery was later made independently by Copernicus after people had forgotten that it had already been made. I love that.
Yes.
Start out with the ancients, and yes, then people forget, and then Copernicus does it again. But way later, we are going back through with archaeology, looking at the discoveries we're making on the ancient sites, and we're like, wow, they already knew this a long time ago. So he says, now the next question that came up for study was exactly how do they go around the sun? That is, with exactly what kind of motion? Do they go with the sun as the center of a circle, or do they go in some other kind of curve? And how fast do they move, and so on? This discovery took longer to make. The times after Copernicus were times in which there were great debates about whether the planets, in fact, went around the sun along with the Earth, or whether the Earth was at the center of the universe, and so on. Then, a man named Tycho Brahe.
Tycho.
Is it Tycho?
Yeah.
Okay. So Randall's saying it wrong?
Well, that's how Feynman says it.
Okay.
He says Tycho.
That's what I thought it was Tycho.
Well, randallswrong.com, folks.
Randalliswrong.com. I don't know. Okay. Tycho Brahe evolved a way of answering the question. And what's interesting, as I was looking into this, I was reading through this, and then I'm like kind of researching a little bit, reading about it. And Tycho was a geocentrist. He thought that he was going to show that everything went around the Earth.
This is great.
Yeah.
Because he ends up doing good science.
Yeah.
And it shows something completely different.
That's right.
I love it.
So he thought that it might perhaps be a good idea to look very, very carefully and to record exactly where the planets appear in the sky. And then the alternative theories might be distinguished from one another. And this is the key of modern science. And it was the beginning of the true understanding of nature. This idea to look at the thing and to record the details and to hope that in the information thus obtained might lie a clue to one or another theoretical interpretation. So Tycho, a rich man who owned an island near Copenhagen, outfitted his island with great brass circles and special observing positions and recorded night after night the position of the planets. And it is only through such hard work that we can find out anything. So, again, it's interesting here. And then, Feynman starts talking about Kepler. And again, when I was reading about this, Tycho was like Kepler's mentor. Right?
Really?
So let me continue a little further here, and then I'll talk about this. So he says, when all these data were collected, and they came into the hands of Kepler, that would be Johann Kepler, who then tried to analyze what kind of motion the planets made around the sun. And he did this by a method of trial and error. At one stage, he thought he had it. He figured out that they went around the sun in circles with the sun off center. But then Kepler noticed that one planet, Mars, was 8 minutes of arc off, and he decided this was too big for Tycho to have made that kind of an error, and that this was not the right answer. So, because of the precision of the experiments, he was able to proceed to another trial and ultimately found out 3 things. Yeah, so it's interesting, like reading how Feynman is expressing it here. But then I was just going and reading other articles about this particular thing, Kepler's laws and all that kind of stuff, and they were saying that Tycho wanted to prove geocentrism. Mm-hmm. But the way he went about that was like we were just talking about. He said, okay, I'll make a whole bunch of very detailed observations first. He had in mind where he wanted to go with his observations, but that he wanted geocentrism, geocentrism to be right. But he gives Kepler the data for Mars, and he's like, here, work on Mars. Right, thinking that that would kind of slow him down or something like that. But Kepler, working on Mars, sees all these errors and says, "Okay, errors in the ideas," and says, "Okay, well, I know that Tycho's not that far off in his observations." Right. And so he's able to use that to prove heliocentrism instead of geocentrism, because Tycho was actually trying to keep him from proving the theory that he wanted. Right, he proved a different one.
Yeah,
it's interesting.
And I think the point of the precision of the experiment is really important too. It's like you can make observations, but if it's sort of lazily done and you don't especially in this case, because you're trying to mark exactly where they are in the sky and measure that in degrees of arc
Yeah.
over time. If you do let it get off by a few minutes, or you're a little bit lazy with the time, timekeeping and all that, then you couldn't come up with the right answer.
Right. That's right. Yeah.
So it's when you're looking into physics in any way, and you're trying to see like, oh, here's some people who might have a good idea. How precisely are they recording their experiments and publishing that for other people to go through?
Yeah. That's right.
Other people who have different ideas and different abilities and different talents.
Yeah. Yeah, it's really key on this that it starts with a bunch of detailed observations, like you're saying.
Yeah. And then the data being recorded and given to other people to analyze.
Yeah, that's right.
If that's not happening, in other words, this is not science.
Yeah, that's right.
Or not good science.
Not good science. Okay. So first, Kepler finds out that the planets went in ellipses around the sun with the sun as a focus. So the next question is, in going around the ellipse, how does the planet go? Does it go faster when it is near the sun? Does it go slower when it is farther from the sun? Kepler found the answer to this too. He found that if you put down the position of a planet at two different times, separated by some definite period, let us say 3 weeks, for example, then in another place on its orbit, two positions of the planet again separated by 3 weeks, and then you draw lines from the sun to the planet, the area that is enclosed in the orbit of the planet and the two lines that are separated by the planet's position 3 weeks apart is the same in any part of the orbit. So, like, to give this a different description, like, at any point where the planet travels in its orbit, if you think of that as a triangle, basically, with the arc of the orbit
as one side,
and then two lines going towards the sun, which would be at the center of the ellipse as the other two sides, then it doesn't matter where in the orbit you do this and how fast the planet is traveling, it always equals the same area enclosed between those three lines.
Right. So when the planet is closer to the sun and traveling much faster, the angles of the triangle are more obtuse.
Yeah. And
when it's far away and traveling slowly, it's a very acute angle.
Yeah, but the distance.
And a long triangle, right? And a long, narrow triangle. And then the other one is a short, fat triangle, and they have the same area.
Yeah, the same area. Cool. As long as the time is the same, as long as both points in the orbit are 3 weeks apart or 2 weeks apart or 1 second, you have the same area within the triangle, no matter how fast the planet is traveling in that orbit. Now, this is another thing I found when I was going through this. This is always idealized. This is in an ideal system. So in other words, Kepler had to see this information through the errors, which is interesting. Maybe we'll get into that because
oh my God, look at this device. The watcher just posted a drawing of Tycho's great brass rings.
Oh yeah,
and look at this design on this thing.
Looks like he's doing magic, doesn't it?
It does. 1, 2, 3, 4, 5. It's a 6-pointed star.
Yeah.
Wow, this is really cool. Can we post this in the show notes?
I can probably put that in the show notes, yeah. So, several years later, Kepler found a third rule. So it took him years to figure this last one out, which was not concerned only with the motions of a single planet around the sun, but related various planets to each other. It said that the time the planet took to go all around the sun was related to the size of the orbit, and that the times varied as the square root of the cube of the size of the orbit. And for this, the size of the orbit is the diameter across the biggest distance. So in other words, it's like the greatest diameter.
Right.
But it's actually you do the calculations using the radius when I was doing the math for this. So Kepler then had these 3 laws, which are summarized by saying that the orbit forms an ellipse, and that equal areas are swept in equal times, and that the time to go around varies as a 3/2 power of the size, which is the square root of the cube of the size. Okay. So I did this. I I sat down and I was like, well, I want to try this out, And when the way it's expressed now is basically just p squared equals a cubed is the way it's expressed now, which is basically means period, the square of the period, or in other words, the length of time of the orbit, that's the period, is equal to the cube of the radius of the greatest distance.
Okay.
So the first thing you notice when you look at this is when you see that p squared equals a cubed, a being the radius of the greatest distance of the ellipse. The only way to make that statement true numerically is to make them both equal to 1.
Huh.
So you start.
But that doesn't really matter, right? When you
it does matter. Because this is the problem. The period is a measurement of time.
Yeah, and the other one is a measurement of distance.
So
I have this problem with I'm sorry, keep going.
Yeah. So the only way to make this work is it's not the only way, but you just start out and say, okay, if p squared has to equal a cubed, well, when they're both 1, it works. It does. Because p1 squared is 1 and 1 cubed is 1. 1 equals 1. Yes, statement is true, mathematically speaking. You see what I'm saying?
Okay.
So all I have to do is say, well, but what I really want to know is how many days or years or miles, whatever,
Yeah,
But
yeah.
all I say is, well, let's take a known system, the Earth, for example, where we have these. We know how many miles it is from the sun, and we know how many days or seconds or minutes or whatever units you want to use. So then I can say that for the Earth, it's 1 equals 1. Okay? In other words, however long it takes the Earth to go around the sun is equal to the cube of its radius from the sun, or distance from the sun. That's all you have to say. Well, 1 equals 1 is easy now. 1 year equals 1 astronomical unit.
Okay.
So that gives you the units that you need to use for this calculation.
Okay.
So in other words, I just make the distance from the Earth to the sun equal to 1, which is, we do
1
have that measurement,
astronomical
1 AU. And the period of its orbit, 1. Well, we have that as well, 1 year. So I took that and I was like, okay,
do Mars.
yeah. So I did Mercury, I did Mars, and I did Jupiter. It's very close. It's close enough to where you can see that there is a relationship.
Okay.
I mean, it's really close. Based on, and I assume that because I'm obviously getting the numbers from just doing basic Google searches, like how far away is Mars from the sun? How far away is Jupiter from the sun? How far away is Mercury from the sun?
At its greatest distance.
Yeah.
Yeah.
And then I convert that to AU. Well, they give it to you in AU.
But the problem with that is that the sun is in one of the foci of an ellipse, not the center.
That's right. Yeah, so they're giving me the average distance. That's what the AU is, right? The average distance. In other words, that's somewhere between the shortest and the largest distance that they are from the sun. But I'm still, when I did the calculations, you can see that it is very close. In other words, there is obviously a relationship there, but there's not just a problem with the fact that I'm probably not getting very precise numbers. There's also a problem that there's a whole bunch of other stuff in the solar system pulling on everything all the
Right,
time.
yeah.
So it's not going to be exact,
It's
right?
the third body problem.
Yeah, it's the 3-body problem. But what I'm saying is
Three-body
that
problem, yeah.
for Mercury, when I did the calculation, I got 92 days roughly of Mercury's period of its orbit, because I was using the distance from the sun and solving for its year just to see if it worked.
Okay.
And I got 92 days with, a huge decimal. And the actual period is 88. That's really close.
Okay.
Okay. And then I did Mars and I got, I don't know, I got 600 and something, and it's 600 and something.
Okay.
And then I did Jupiter and I got 11.8 something years, and it's 12 years roughly, so in other words, you can see that there is a relationship.
Okay.
There's errors, but that's accounting for the fact that I'm
They're
not
all
doing this in
pulling on
heaven.
each other. Yeah.
And the fact that I'm getting rough estimates of numbers, not the exact ones that Kepler was working with.
Gotcha.
Kepler, having all of Tycho's very precise measurements from that time, could probably get closer approximations and see the relationship better than I could. But even so, using approximate numbers, where I'm like, Mercury is 0.4 AU, but it's not, right? It's going to be some really long.
Yeah.
And, Mars is, I can't remember what they are now, 1 point something, and Jupiter is 3.7 something, But the point is that just doing those 3 planets, starting with 1 equals 1,
Yeah.
it's easy to see that there is a relationship. I thought that was really cool.
That is cool.
But that's kind of what he's talking about with the math, is like you see that formula, and the first thing you have to do is understand how to use it. Right? Because if you start out, how far is the Earth from the sun? Well, let's see, it's 90-something million miles. So you put in 90-something million for A, and then you get the cube of that. And you're like, how many days does the Earth go around the sun? 364.25, and then you put that in as P and square it. They don't equal each other.
Yeah.
So that's what I'm saying, is the first thing you have to do is start out with what variables.
You have to get a unit of measure.
Yeah. What variables, and then what it basically tells you have to start with them equaling 1.
Gotcha.
That's the only way that's the only number for which that
I understand.
statement equals. Yeah. So
that's
anyway,
weird.
Yeah. Maybe I just too much detail there, but that's how it happened.
No,
in my head.
you've broadened my conceptualization of this mathematical formula, because I did not understand it from just reading the book or listening to the lectures. So that's cool, man.
But Feynman describes it in the way that Kepler describes it, which is basically he's giving it to you. He's not giving it to you in the same way that I saw it, right? Which is basically P squared equals A cubed. I mean, he does say that, but he calls it the square root of the cube of the size. That's right. Which is, he's basically he's solving for P there. You see what I'm saying? He's solving for the period by taking the square root of the cube.
Yeah.
So
that's weird.
Yeah.
I don't know how it works.
I don't know. Maybe this is too dense. But the point is that I read through this and I was like, okay, this is cool. Let's test it out. And I did. I tested it for a couple of the planets, and you can see the relationship.
That's cool.
That there is this relationship. It's just, to me, mathematically fun to understand how you have to start, and then once you understand, okay, this is how I can get rid of the units, because the units are arbitrary.
Yeah, for sure.
Okay, let's take a break.
All right, we'll take a break.
Question was, what makes him go around? So how can we understand this in more detail? Or is there anything else to say? In the meantime, Galileo was investigating the laws of motion. Incidentally, at the time of Kepler, the problem of what drove the planets around the sun was answered by some people by saying that there were angels behind here beating their wings and pushing the planet along around orbit. As we'll see, that answer is not very far from the truth. The only difference is that the angels sit in a different direction and where wings go in it.
Their wings push inward.
Yeah.
Yeah. Welcome back, Brothers of the Serpent Podcast. Still going through a character of physical law of gravitation, and that again was Dr. Feynman. Speaking about the next part, we're moving on to Galileo here. So he says, in the meantime, Galileo was investigating the laws of motion of ordinary objects at hand on the Earth. In studying these laws and doing a number of experiments to see how balls run down inclined planes and how pendulums swing and so on, Galileo discovered a great principle called the principle of inertia, which is this: that if an object has nothing acting on it and is going along at a certain velocity in a straight line, it will go at the same velocity in exactly the same straight line forever. Unbelievable as that may sound to anybody who has tried to make a ball roll forever, if this idealization is correct, and there were no influences acting, such as the friction of the floor and so on, then the ball would go on at a uniform speed forever. The next point was made by Newton, who discussed the question, when does it not go in a straight line? When it does not go in a straight line, then what? And he answered it in this way, that a force is needed to change the velocity in any manner. For instance, if you are pushing a ball in the direction that it moves, it will speed up. If you find that it changes direction, then the force must have been sideways. The force can be measured by the product of two effects. How much does the velocity change in a small interval of time? That's called the acceleration. And when it is multiplied by the coefficient called the mass of an object, or its inertia coefficient, then that together is the force.
So what's a coefficient?
The coefficient is the known value. That's probably the best way to say it. So like the mass of any given object is a known value that you can calculate.
Okay.
So usually that's what they're saying, you know, when you have the coefficient and you're multiplying, some variable is multiplied by a coefficient, then the coefficient is the known value in the calculation.
All right. Thank you, sir.
Yeah. So he says, again, that's called acceleration. And when it is multiplied by the coefficient called the mass of the object, or its inertia coefficient, then that together is the force. So what he's saying there is the inertia coefficient or the mass of the object are the same number. So he says Newton saw from this.
Okay, so he means the mass, or in other words, the inertia.
Inertia coefficient.
Okay, gotcha.
Yeah. Those are the same thing. So Newton saw from this that, to take a simple example, if a planet is going in a circle around the sun, no force is needed to make it go sideways tangentially. So when I read this, I was like, what is he talking about? So what he means is, it's just weird the way he said it. In other words,
tangentially meaning just going off.
Yes, just it stopped going in a circle and continue to go in the direction, a straight line. That there's no force necessary for that to take place, right? Just because, like what we were just looking at.
As long as it's already moving.
Right.
Yeah.
Like what Galileo said, it's going to keep going forever. But if it needs to keep going around the sun, then you do need a force.
You have to have a constant force.
Yeah. So yes, no force is needed to make it go sideways. If there were no force at all, then it would just keep coasting along. But actually, the planet does not keep coasting along. It finds itself later not way out where it would go if there were no force at all, but farther down towards the sun, or in other words, continuing along in its circular or elliptic orbit. In other words, its velocity, its motion, has been deflected towards the sun.
And this is often described as falling.
Yes, it's falling towards the sun.
Right.
The combination of it, the planet falling towards the sun, plus its
inertia
keeping it goes around in a circle. Yeah, right.
And I think of that as the angular momentum, right?
Yeah, the angular momentum. And yes, this is like, it's interesting.
You're on the merry-go-round, and you can feel it. You can feel your inertia pulling you in a tangential line, wanting to go straight.
Yes,
out away from
fly off the merry-go-round and go straight. That's right.
If the center of the merry-go-round had a giant, dense ball there, and it could pull you at the same amount as your,
then you would feel like you were just floating.
You're just floating.
Yeah, that's right. And this is hilarious too, because if you've ever read any of Douglas Adams' Hitchhiker's Guide, he says that the secret to flying is to just fall and miss the ground. And he's totally correct. I mean, it sounds ridiculous, but that's how everything floats.
That's right.
When we go into low Earth orbit, what they're doing, all those satellites and all those astronauts, they're falling, but missing the ground.
That's right. We got to go fast enough to keep missing the ground.
That's right.
It's cool. It's really cool to think of it that way.
Yeah. So Feynman says, so that's what the angels have to do. They have to beat their wings in towards the sun all the time.
That's the force.
That's the force, yeah. But the motion to keep the planet going in a straight line has no known reason. The reason why things coast forever has never been found out. The law of inertia has no known origin. Although the angels do not exist, the continuation of the motion does, but in order to obtain the falling operation, we do need a force, and it became apparent that the origin of the force was, it's weird how he says this again, the origin of the force was towards the sun. That's not the origin of the force necessarily.
Well, yeah. I know what
you know,
mean.
he's talking, yeah. We don't know the origin of the force, but the direction of the force is towards the sun.
Or the vector.
Yeah.
Yeah.
But I love this.
It's
But
fascinating.
you pointed this out to me, and I agree when we were talking about this, that he just like lays it out there that inertia has no known reason.
Yeah, it's fascinating to me that I'm sure there's lots of speculation, or maybe there's some theories or hypotheses that have been presented, but it's just, you don't see this being worked on. Like, at least the science communicators are not putting out like, we're working on ideas about inertia.
Yeah.
And to me, that is like, this has to be some key fundamental aspect of space and time or something. You know,
it
it's
does
like
seem
the fabric
fundamental.
of the universe, the fact that things have inertia.
Yeah. Yeah. That seems to be the zero state, right? That's what's interesting about it, because like what we're looking at here about taking an orbit and that requiring a force, a continuous force acting on the object to keep it in orbit, that's a secondary state.
That's right. Yeah.
The fundamental state of the object is to continue on with its inertial motion, whatever that may be. The thing that Galileo figured out, that basically if it has a velocity and no other forces acting on it, it's going to continue with that velocity in that direction forever.
Once it's there, it's just in a static state. It just doesn't change.
Yeah, that's right.
And the other crazy thing, I know we'll get into this further, but it's like this is another thing that sort of compounds the mystery, which is that two bodies observe, like one observing the other. You can't tell which one's moving and which one's not moving. Like you could say, well, you have a stationary body and there's another body that's passing by.
Yeah.
And there's no real way to tell which one's actually doing the passing by and which one's sitting there.
Yeah, that's relativity.
It's crazy, dude.
Yeah.
So I don't know. But anyway, I'm jumping ahead.
Okay. So, in other words, its velocity and its motion have been deflected towards the sun. So, but the motion, no, I already read that. Okay, so it became apparent that the origin of the force was towards the sun. As a matter of fact, Newton was able to demonstrate that the statement that equal areas are swept in equal times, that's Kepler's thing, was a direct consequence of the simple idea that all the changes in velocity are directed exactly towards the sun, even in the elliptical case. So from this law, Newton confirmed the idea that the force is towards the sun, and from knowing how the periods of the different planets vary with the distance away from the sun, it is possible to determine how that force must weaken at different distances. He was able to determine that the force must vary inversely as the square of the distance. So that's really interesting. So Newton is looking at Kepler's work.
And that makes an exponential curve, right? If you were to graph that inversely as the square of the distance.
Right.
Since you're always squaring the distance, it's if you just take points as you get further and further away and you keep squaring it, it's going up by orders of magnitude, basically.
Yeah. That's right.
What do you call that kind of gain or something? I don't know I don't know the mathematics.
Oh,
it's logarithmic, or it's
not logarithmic. It's exponential.
Exponential curve.
Mm-hmm. Yeah, and it's an inverse exponential, so it's going
getting down.
Yeah,
yeah. And
it's
it never
starting
quite
up very high and coming down and curving out.
Yes,
flat.
and it never quite goes away ever.
Ever. That's right. It never reaches zero.
It's cool.
But it's interesting because he was using the changes in velocity based on, he's looking at this force or whatever, and he's able to say, okay, so because I already can start with the idea that it's going to keep going forever if nothing acts on it, but I know that they're not continuing to go forever. They're actually curving around something. Then I can take these previous observations, the
Yeah.
data, and look at the curves that they're making. And then that can give me an idea about the strength of the force in any given special circumstance, like the Earth, for example.
Yeah.
And then he can see, well, how does that apply to these other bodies out in different places? And he can look at the data for those and see, oh, well, here's how the force actually must get weaker. And here's the way it gets weaker, because you can start to graph it.
Yeah.
And then you can see, well, that's an exponential curve, and it roughly approximates the inverse of the square of the distance.
It's cool. So glad nerds exist.
All right, where was I? Okay, but people had seen in telescopes Jupiter's satellites going around Jupiter, and it looked like a little solar system, as if these satellites were attracted to Jupiter. The moon is attracted to the Earth, and it goes around the Earth and is attracted in the same way. And it looks as though everything is attracted to everything else. And so the next statement was to generalize this and say that every object attracts every object. If so, the Earth must be pulling on the moon, just as the sun pulls on the planet. But it is known that the Earth is pulling on things because you're all sitting tightly in your seats in spite of your desire to float in the air. The pull for objects on the Earth was well known in the phenomena of gravitation, and it was Newton's idea that maybe the gravitation that held the moon in orbit was the same gravitation that pulled objects towards the Earth. In other words, I think what Feynman's trying to point out here is that this is a big leap. In other words, he's generalizing this concept. The same force that's holding the moon up in the sky is the one that's holding you in your seat.
Right.
And we can figure this out, or we can find out if, and he does actually, I didn't mark any of this to read, but he does kind of do this a little bit. You can say, well, let's take the mass of a known object and calculate its the gravitational pull on it here close to the surface, and then we can calculate the same thing for the moon. And if we see this curve, if we say, well, here's the curve of what it's supposed to be. Let's figure out if we get the right numbers for the moon. Because you can use that to calculate the moon's mass if you know the Earth's mass and the gravitation, the constant. So, and the numbers kind of work out. They're very close.
Yeah.
Again, none of this is precisely exact because we're not operating in heaven. Like the Earth and the moon aren't the only things here.
Right.
Right. But when they're that close, and then you can do it for a bunch of things and sort of get similar numbers that agree with other observations or other ways of looking for that same data, and you see that they're very close, then you see that there is a mathematical relationship.
Yeah.
And he does this with tides, shows how Newton thought about the tides.
Yep.
And it was difficult. Like Kyle and I had this discussion a while back, but it's difficult because you're like, well, maybe the moon causes the tides, but the tides happen twice a day. So if the moon is pulling the water towards you, then there should only be one tide roughly every 24 hours because it's basically about the spin of the planet. But it's more complicated than that.
Because there's tidal forces involved.
Right.
Not meaning ocean tides, but...
Yes, right.
Is that where the term comes from, though? Because because the oceans on the other side of the planet away from the moon are being pulled inversely...
Yeah, less...
to the square of the distance.
Through the distance of the planet, there's a drop off of gravity. So they bulge on that side.
They can fall out a little further.
That's right. Yeah. They bulge on that side because they have less of the moon's gravity acting on them, and so they can go farther out in that direction.
Yeah, that's cool.
So the big tide is on the moon side, and the small tide is on the
opposite
side. Yeah, and that is explained, roughly speaking, with the inverse of the distance from the moon. So a lot of other things became clear. How the Earth is round because everything gets pulled in. How it is not quite round because it is spinning and the outside gets thrown out a little bit. And how this balances and how the sun and moon are round and so on. So that's another interesting thing. You don't necessarily connect these things, but once you realize that from the center of any given mass, you can think of the gravity falling out in a coefficient, and it's going to be pulling on everything equally, and it's the same force. It's just one thing. Then you say, well, yes, everything will, if it's big enough, it's going to basically be a sphere. Mm-hmm. I find that interesting, and that's how you can look at Phobos and Deimos, Mars's moons, and they're not big enough. They're potatoes. They're not big enough to be spheres.
That's right. Because you got to overcome the strength of the materials.
The strength of the material, yeah. But their
The
gravity
force has to be
their gravity is so low that if you were standing on one of them, one jump would put you in orbit around it, right?
Yeah.
You might actually get escape velocity.
Yeah. Gotta be careful.
Yeah, right.
Just use a tiptoe jump.
So as science developed and measurements were made more accurate, the tests of Newton's law became more stringent. And the first careful tests involved the moons of Jupiter. This is amazing.
I love this too. Yeah.
By accurate observations of the way the moons of Jupiter went around over long periods of time, one could check that everything was according to Newton, and it turned out not to be the case. The moons of Jupiter appeared to get sometimes 8 minutes ahead of time and sometimes 8 minutes behind time, where the time is the calculated value according to Newton. So it was noticed that they were ahead of schedule when Jupiter was close to the Earth and behind schedule when it was far away, which is a rather odd circumstance. Mr. Romer, is that how he says that guy?
Not sure.
Okay.
I don't remember.
Yeah, it would be Olaus Romer, a Danish astronomer. So him having the confidence in the law of gravitation came to the interesting conclusion that it takes light some time to travel from the moons of Jupiter to the Earth. And what we are looking at when we see the moons is not how they are now, but how they were the time ago it took the light to get here. So when Jupiter is near us, it takes less time for the light to come. And when Jupiter is farther from us, it takes a longer time. So Romer had to correct the observations for the differences in time and by the fact that they were this much early or that much late. And in this way, he was able to determine the velocity of light.
That's great. So cool.
This was the first demonstration that light was not an instantaneously propagating material.
I find that interesting that they're talking about it being a material.
Yeah. Yep. Well, and I mean, they have gone back and forth on what it is.
Of course, yeah.
Like later, like he talks about how Einstein and one of his colleagues decided, like, well, let's call light these little particles.
Right. A material.
Yeah. And they must have mass of some kind because they're affected by gravity. So there is material involved.
That's
here.
right. Yeah. It's just, I don't know. It's one of the ways that Feynman talks about stuff. It just makes you like, wait.
Yeah.
Yeah. We're getting nailed by this material all the time.
That's right. So Feynman says, I bring this particular matter to your attention because it illustrates that when a law is right, it can be used to find another one. If we have confidence in a law, then if something appears to be wrong, it can suggest to us another phenomenon. If we had not known the law of gravitation, we would have taken much longer to find the speed of light because we would have not known what to expect of Jupiter's satellites. This process has developed into an avalanche of discoveries. Each new discovery permits the tools for much more discovery. And this is the beginning of the avalanche, which has gone on now for 400 years in a continuous process, and we are still avalanching along at a high speed. So that's interesting because, again, you know, we've as we talk about this, you can see that and maybe this is kind of your point about the math, is that I keep saying it's roughly correct. In other words, you can see a relationship in the numbers, and that allows you to say, well, here's the idealized version expressed in a mathematical formula, or as Newton would do it, expressed geometrically.
Yeah.
But like you're saying, you have to be the kind of person that can have that insight by looking at a bunch of numbers that are basically the results of observations. And as time goes on, the observations get better, more accurate. And so maybe you can recognize more or different relationships, you know, or you can use them to check, are these relationships that were recognized 400 years ago still relevant?
Yeah.
Do they still work? But what he's saying here is that because they were so confident in the law of gravitation, they were able to discover the speed of light by seeing an error in their predictions for Jupiter's moons and saying, well, the error can't be in the law, so there must be some other effect taking place here.
That's right.
And he was able to say, well, maybe it's how long it takes the light to get here for us to see it. And he has that intuition. Why? Because it's 8 minutes ahead when it's close and 8 minutes behind when it's far.
That's consistent.
Yeah. And he's like, okay, so this problem has something to do with distance, not the law of gravitation.
Right.
It's got something to do with how far.
Distance from the observer.
Right. Distance from the observer for how Jupiter is. So he makes this intuitive leap and say, well, maybe it has something to do with how long it takes the light to get here. And then he does a calculation and he finds the velocity of light.
You get the velocity of light, and then you can look somewhere else and check.
Right. Yeah. You can
see if it applies.
Yeah, you can say, well, let's use the laws of gravitation to calculate Saturn's moons, and then look
Right.
at that, and then, well, wow, it takes 16 minutes or whatever, however far away Saturn
Right.
is. Yeah.
I love that just the principle there that once you discover a law that is right,
Yeah.
it can lead you to other laws. That's just great. I love it.
Yeah. It does take a little bit of, faith in the law, though.
Well, yeah.
Like how do you what happens when you what happens if you find something that doesn't agree with your law, but it's actually showing you a problem with the law and not implying a new phenomena, but you assume
And that
because you're so
happens.
confident in the law that you're so confident in the law that you're just like, well, this must be a different phenomenon.
But everybody's searching in both areas, right? You see this discrepancy, and you're like, okay, somebody has confidence in the law. They're looking for something new, and somebody else is like, this law is BS. Like, we got to fix it.
We got to fix the law.
So there's people doing both things.
Yeah.
So you could, it's because you're sharing the knowledge and the data and and the experiments and the results and all of that stuff.
Yeah.
Again, this is
the process.
you've got to get precise data by doing experiments very well, and then you have to put that data out there to be analyzed.
And a lot of the times by experiments, especially with this stuff, what we're talking about is just like precise observations.
Right.
I mean, Galileo was doing experiments like rolling things and dropping stuff. But
Well, it's also doing an experiment to set up an observatory. That's an experiment.
yeah. Yeah. But then you have to wait for the universe to do the thing you want.
Yes.
So Feynman says another problem came up. The planets should not really go in ellipses because according to Newton's laws, they are not only attracted by the sun, but they also pull on each other. A little, only a little, but that little is something, and it will alter the motion a little bit. Jupiter, Saturn, and Uranus were big planets that were known, and calculations were made about how slightly different from perfect ellipses of Kepler the planets ought to be going by the pull of each on the others. And at the end of the calculations and observations, it was noticed that Jupiter and Saturn went according to the calculations, but that Uranus was doing something funny. Another opportunity for Newton's laws to be found wanting, but take courage. Two men, Adams and Leverrier, who made these calculations independently and almost exactly at the same time, proposed that the motions of Uranus were due to an unseen planet, and they wrote letters to their respective observatories telling them, "Turn your telescope and look there and you'll find a planet." "How absurd," said one of the observatories. "Some guy sitting around with pieces of paper and pencils can tell us where to look to find a new planet." But the other observatory was more, well, the administration was different, and they found Neptune.
I love that.
Yeah. He's giving a little dig there at the the observatory that didn't listen to the guy. Some Johnson sitting around with paper can tell me where to find a new planet. Don't tell me where to point my telescope. So the question is, how far does this law extend? Does it extend outside the solar system? So here we're gonna go through this, and I'll try to do some descriptions. But he basically is showing a series of images, plates he calls them. So he says, and I show on plate 1 evidence that the law of gravitation is on a wider scale than just the solar system. Here is a series of 3 pictures of a so-called double star or binary star. There is a third star, fortunately, in the picture so that you can see that they are really turning around and that nobody simply turned the frames of the pictures around, which is easy to do in astronomical photographs. So yeah, there's 3 images. There's one star that's stationary basically in the lower right of the image, but on the upper left you can see a binary star, and starting from July of 1908 and going all the way through July of 1920, they've taken photographs and you can see that there is an orbit taking place. The smaller binary companion is orbiting in an ellipse around its larger binary companion. And Feynman talks about he discusses how it's not quite right, but that's because the orbit is tilted and all
Yeah,
that stuff.
they look at it and it's like, well, it's not quite an ellipse.
Yeah.
But then if you look at an ellipse from a skewed angle,
Yeah.
it could look like a circle.
Right. That's right. So he says it is evident that they are attracting each other and that they are going around in an ellipse according to the way expected. So how about a bigger distance? This force was between two stars, but does it go any farther than distances which are not more than 2 or 3 times the solar system's diameter? So this is great. The reason I'm including this is because what Feynman is showing you here is that they're not just taking for granted that this works everywhere. Once you've got the idea that, okay, so the solar system seems to work on this law of gravitation thing and, Kepler's laws, Newton's ideas and all this stuff, and we're saying, okay, it seems to apply broadly across all the planets. There's all these interesting things. There's relationships, inverse squares, all this kind of stuff. The question is this a local phenomena? Or can we actually say that, can we look out in the universe and see, does it apply everywhere? Or at least in other structures? So that's what he's showing you here. So he's asking the question, does it apply to bigger distances? Not just regions of the solar system or even this binary star, which is, a couple of times the size of the solar system, but let's see if we see it in larger structures. So he shows something in plate 2. He says this is 100,000 times as big as the solar system in diameter. It is a tremendous number of stars. So it's a globular cluster. It's a huge one. Very interesting photograph he's got here. And he says this large white spot is not solid. It appears like that because of the failure of the instruments to resolve it. But there are very, very tiny spots, just like other stars, well separated from each other, not hitting one another, each one falling through and back and forth in this great globular cluster. It is one of the most beautiful things in the sky. It is as beautiful as sea waves and sunsets.
That's cool.
And he means it is as beautiful as sea waves and sunsets in the fact that there are these patterns and repetitiveness, and that also you can see physical laws taking place.
Right, it's following this same simple
And I mean, talk
principle.
about the 3-body problem. Look at that thing. I'm
crazy.
pointing it out to Kyle. This cluster that star cluster that he's got on here, it looks like a paint spatter. It's got so many freaking stars.
Yeah.
And there's a common center of mass, and all these things are flying around in there. And you wonder
in what would be in a simplified version of 2 of them in ellipse.
Right. Yes.
But because they're all pulling on each other and trying to make ellipses out of everything, it's like these crazy curves and changing velocities and all this stuff, following all that same simple.
Yes, but they still follow like the same area over times of orbit. Yeah,
yes.
It's craziness. It's really awesome. And that star cluster is, of course, like he said, 100,000 times the size of the solar system. So there you have an object where you say, okay, it does apply across this size of a vast distance. Yeah. So he says the distribution of this material is perfectly clear. The thing that holds this galaxy together, so now he's showing a picture of a galaxy, is the gravitational attraction for the stars for each other. The distribution of the material and the sense of distance permits one to find out roughly what the law of force is between the stars. And of course, it comes out that it is roughly the inverse square.
And now, he doesn't talk about this, I don't think, but we have dark matter.
Right. He doesn't. He didn't mention any dark matter in here yet.
Right.
Yeah. But that's maybe why he's saying roughly.
Right.
So accuracy in these calculations and measurements is not anywhere near as careful as the accuracy we have in the solar system. Mm-hmm. So onward, he says, gravity extends still further. That cluster was just a little pinpoint inside this big galaxy in plate 3, which shows a typical galaxy. And it is clear that, again, this thing is held together by some force, and the only candidate that is reasonable is gravitation. When we get to this size, we have no way of checking the inverse square law. But there seems to be no doubt that in these great agglomerations of stars, these galaxies are 50,000 to 100,000 light years across, while the distance from the Earth to the Sun is only 8 light minutes. Gravity is extending even over these distances. And then in plate 4, we have evidence that it extends even farther. In this plate, we have what is called a cluster of galaxies. They are all in one lump and analogous to the cluster of stars, but this time what is clustered are those big babies shown in plate 3. So in other words, he's showing you a cluster of galaxies where you're looking at another burst, but it's a bunch of dots, and every dot is a galaxy.
Each dot is 100,000 light years across or whatever.
Yeah.
Crazy.
So he says this is as far as about 1/10 or maybe 1/100th of the size of the universe, as far as we have any direct evidence that gravitational forces extend. So I think that would be at that time.
Okay. Yeah.
At that time, I think those two things are outdated. The distance that galaxy cluster, or that galaxy cluster would be 1/10 or 100th of the universe. I think it's expanded since then.
Or our idea,
Our understanding of the size, and probably we have more evidence of very distant gravitation working. Because, you could see those pictures now of these huge structures that include billions of galaxies. So it becomes weaker and weaker inversely as the square of the distance, divided by 4 each time you get twice as far away, until it is lost in the confusion of the strong fields of other stars. So what he's saying here is...
I love that. That's a very good description of the inverse square proportion.
Yeah. That's right.
4 times weaker every time it's twice as far away.
Right. Yeah. I'm sorry. He's talking about the Earth's gravitation here. He says the Earth's gravitation has no edge, although you may read in papers that something gets outside the field of gravitation. It just gets weaker and weaker as you get farther away. So together with the stars in its neighborhood, the Earth pulls on the other stars to form the galaxy, and all together they pull on other galaxies and make a pattern, a cluster of galaxies. So the Earth's gravitational field never ends, but peters out very slowly in a precise and careful law, probably to the edge of the universe.
That's cool. The wake? It's the wake of the sun.
It is the wake of the sun. So the law of gravitation is different from many of the others. Clearly, it is very important in the economy or in the machinery of the universe. There are many places where gravity has its practical applications as far as the universe is concerned, but atypically the knowledge of the laws of gravitation has relatively few practical applications compared with the other laws of physics. And I think what he means by practical is like, we haven't been able to use this law to build cool things. I think that's what he's talking about.
I mean, okay, it doesn't have very many. One of the important ones I would assume is like rocketry.
Yeah, he does mention that. Yeah. It's interesting how he goes through this. Like, I think what he's thinking of in his mind, because you have to think of, like, he's up there on stage. What is he thinking of? He's thinking of, like, recent nuclear physics. Like, we built all this crazy stuff.
Yeah, absolutely.
Like electricity, right?
Tons of
like, okay, so we understand gravity, but it hasn't resulted in anti-gravity yet. Like, we haven't, all these applications, So he says, this is one case where I've picked an atypical example. It is impossible, by the way, by picking one of anything, to pick one that is not atypical in some sense. This is the wonder of the world. The only application of the knowledge of the law of gravity that I can think of are in geophysical prospecting, in predicting the tides, and nowadays, more modernly, in working out the motions of the satellites and planet probes that we send up, and so on. And finally, also modernly, to calculate the predictions of the planet's positions, which have great utility for astrologists to publish their predictions and horoscopes in the magazines.
That's great. It's good. All right. Well, we're going to take another break. We'll be right back.
Right. Final break.
Thanks.
There is one example of a star patch, a light that grew in a place within 200 days. So that when it was in the same kind of a condition of a gas cloud, when the gas collects too much together by gravitation, stars are born. And this is the beginning of new stars. So the stars belch out dirt and gases when they explode sometimes, and the dirt and gases then collect back again and make new stars. Sounds like perpetual motion.
And we're back, ladies and gentlemen, for the final segment here of Brothers of the Serpent podcast. Going through the character of physical law, first lecture by Dr. Richard Feynman. And I want to mention that these bumper songs are all instrumental versions of the masters of the new $50 Dynasty album, Precession.
Oh, yeah.
which I will be releasing these instrumentals to the Dynasty Patreon at some point pretty soon. Anyway, that's what they are. I love them, and I hope you love them. And this latest one is called Wake of the Sun, which I love the idea of that. And that's kind of what Feynman is talking about a little bit.
The Wake of the Sun. So the next section here, I didn't mark anything to read because it's a little, I think that the best way to do this, because he's describing an experiment. And Kyle's actually described it to me several times, so I think that I'll just let you do that. This is the experiment by Cavendish to, weigh the Earth. Yeah,
so basically he suspends like if you imagine...
so the goal here was to find out
if two objects will attract each other.
Right. On the small scale.
Yeah.
Feynman was just like, okay, we see it out in the universe and on huge scales. Does it actually work like, do small things also do this?
Yeah.
So that's the point of this experiment.
So imagine you're hanging a large dumbbell, or say like a curl bar with big weights at the end, right? The huge weights on either side are lead balls.
Yeah.
Like a very dense material.
Yeah.
And you're suspending it by a thread in the center so that it's balanced. And then if you're looking at this thing straight on, the two balls, one is on the left side, the other's on the right. Let's say the right side lead ball, you place in front of it a huge, giant lead ball. And then on the left side, you put behind that one another huge, giant lead ball and see if the giant lead balls pull the two smaller lead balls on the curl bar into, like, to twist clockwise.
Yeah.
Essentially. I hope that's a good explanation. There's a simple diagram of it in the book, but it actually did. And the thread that they hung it by was a quartz fiber, and quartz is piezoelectric. So if there's any mechanical force acted on the quartz, you will detect it via that quartz producing an electrical signal.
Yeah.
And they noticed that when you put the giant lead balls close to these things, there was an electrical signal coming from the quartz fiber.
Yeah.
In other words, they were attracting each other.
Right. Now, you could think of the experiment like...
We also know that everything is magnetic.
Yeah.
Like magnetism is... Mm-hmm. It's like, I've heard this said that everything has some degree of magnetism.
Yeah, some latent magnetism, yeah.
So, did they correct for that? Probably.
Yeah, probably.
In other words, there was some signal due to the magnetic attraction between the two balls.
Yeah.
But there was maybe too much.
Yeah.
And the amount of signal that was the too much was equivalent to the force that was the product of the two masses varying inversely by the distance between them, perhaps.
Yeah.
I don't know. He doesn't go into detail about that. But
right. I was thinking about this experiment, that the nature of the setup is, I thought about that. We don't need the sands of time. It's the final segment.
Oh, okay. Yeah, all right.
We're just going to go until we're done.
Looking at it draining away there.
Yeah. My job was to set up the sands of time, and I didn't, and Kyle just started it going. So the nature of this experiment with the twisting is because of the physical function of the method of measuring. That's what I thought, because when you look at this, like Kyle described, you could have made it simpler by hanging a single lead ball from the thread and then just putting a huge, massive lead ball next to it. But that doesn't allow you to measure in the way that you want a very tiny amount of attraction to that single lead ball to the other one. The way you want to measure it is using this quartz fiber. And if you just let it swing, the quartz fiber is not getting any specific mechanical change to it. It's just doing like a pendulum motion. The quartz fiber could actually
stay straight.
So you need it to twist. So to set up one that twists, you hang the dumbbell thing from the quartz fiber with two lead balls at either end of the dumbbell, and then you need a giant lead ball in front of one of the dumbbell balls and another one behind it, and that allows it to twist the quartz fiber. So the nature of the experiment is made more complicated by the way we can measure the forces.
It's ingenious too.
It is genius.
I
yeah,
think it's cool.
Yeah.
and I often make fun of that experiment. When we're talking about gravity,
Oh, yeah.
it's like, what is gravity? Oh yeah, they know what it is because they put lead balls close to each other and they pulled on each other a little bit.
That proves the law of gravitation, or it's evidence for the law of gravitation.
Absolutely.
It doesn't have anything to do with any theories of gravity.
Yeah, it's just a way to see, like, does it apply at smaller scales?
Yeah.
And apparently it does.
Yeah, and it's also Feynman goes into a little bit about why Cavendish, who is the one who set this up, he called this experiment weighing the Earth. And there's an interesting connection here with this idea. First, Feynman says that, we wouldn't let our students say that today. We would call it measuring the mass of the Earth. But indirectly, this experiment was the first determination of how heavy or massive is this ball of material upon which we stand. Feynman says that. Mm-hmm. It's an amazing achievement to find that out, and I think that is why Cavendish named his experiment weighing the Earth instead of, quote, determining the constant in the gravitational equation, unquote. He incidentally was weighing the sun and everything else at the same time,
right?
Because the pull of the sun is known in the same manner. And of course, the gravity, if the inverse square law is true, of everything in the universe is detectable by that quartz fiber. Or I should say, it's acting on the masses in question. It may not be detectable through the experiment.
It may not be, the experiment doesn't have a high enough resolution.
Yeah, that's right. Okay. So one thing Feynman says...
But this is the other thing we often talk about real quick about the mass, is that I wonder, and of course, folks, like, I don't know anything, but I wonder that is the mass just correlated?
Yeah.
Because it always seems like when you hear the physicists talking about it, that the mass is almost like, they look at it like the mass is the source, or at least...
That's how it seems... That's what it seems like how it comes across when they're talking about it, or when you hear science communicators talking about it. Mm-hmm. But I do wonder, like you're saying, do they, in their own minds, know that? Because when I'm reading away Feynman, he doesn't ever seem to do that indication. Mm-hmm. He's just like, here's how we check to see if this is still true with these tiny masses.
The value of the force is correlated to its mass all the time.
Yeah, and it is.
Yeah.
And it's always close.
Right.
But it's not perfect, Yeah, so they can keep saying like, well, it's close. But what Feynman says here is like, well, you're also weighing everything else in the universe. Yeah. And so you can maybe stack on an assumption and say that the reason it's just close is because there's all this other stuff. There's this very complicated system inside of which we're doing the experiment.
Yeah.
Okay, so one thing Feynman says is particularly interesting. The inverse square law appears again in the electrical laws, for instance. Electricity also exerts forces inversely as the square of the distance, this time between charges.
And so magnetism also.
And one thinks perhaps that the inverse square of the distance has some deep significance. But no one has ever succeeded in making electricity and gravity different aspects of the same thing. So when I read this, I was kind of getting the idea that he's saying two things there. It sort of comes across like it's one thing, but he's saying two things, like that there is a deep significance to this inverse square law. Mm-hmm. But nevertheless, no one has ever succeeded
found any other connections.
Right. Yeah, that's right.
The inverse square law is also applies to waves propagating in space.
Yeah.
So and also, like, if you measure the, I don't know exactly how to describe it, but like, say you have a string vibrating, right? You take this, a very simple vibration, the string vibrating, and you measure the, I don't know if it's the energy or the force or the whatever of the center of the vibrating string. Mm-hmm. And then as you move closer to the nodes at either side, it's...
Oh, you're measuring, if you measure the amplitude of the motion at the center.
It's also the inverse squares to the distance. It's the same. It's weird.
It does. See, that's what he's saying. It does imply some deep significance to that particular relationship.
I know. It's cool.
And the fact that it's like, it's inverse. Sometimes it's just, it's directly, it's proportional to the square, or it's inversely proportional to the square. Mm-hmm. But these things seem to apply across multiple phenomena.
Isn't the other one, the other way to describe it is something about it's directly to the mass and inversely to the square of the distance, or something like that.
Yeah.
Directly as the product of two masses.
Right. Yeah.
Inversely as the square of the distance between them.
Yeah.
Yeah.
Okay, so no one has ever succeeded in making electricity and gravity different aspects of the same thing. Today, our theories of physics, the laws of physics, it's interesting that he says both of those things there, are a multitude of different parts and pieces that do not fit together very well. We do not have one structure from which all is deduced. We have several pieces that do not quite fit exactly yet. That is the reason why in these lectures, instead of having the ability to tell you what the law of physics is, I have to talk about the things that are common to the various laws. We do not understand the connection between them. But what is very strange is that there are certain things which are the same in both. Now let us look again at the law of electricity. The force goes inversely as the square of the distance. But the thing that is remarkable is the tremendous difference in the strength of the electrical and gravitational forces. People who want to make electricity and gravitation out of the same thing will find that electricity is so much more powerful than gravity that it is hard to believe that they both could have the same origin. So how can I say one thing is more powerful than another? It does depend on how much charge you have and how much mass you have. So you cannot talk about how strong gravity is by saying, well, I take a lump of such a size because you chose that size. So again, this goes back to kind of what I was trying to explain in the first segment about
how you have to start with one.
Yeah, like you can't, the units of measure are a problem here, or like deciding, well, the Earth is this thing, whatever. You're starting out with something in nature, but when you're describing it mathematically, you kind of have to abstract yourself away from that and say, well, can I explain this generally without using...
So saying size is just a variable.
Yeah.
And trying to make it work that way.
Yeah. And then picking a very simple number and seeing if the equation works, and then seeing if it does apply across all the complicated systems. Yeah. So that's what he's saying here. You cannot talk about how strong gravity is by saying, well, I take a lump of such a size because you're choosing that size. That doesn't tell you how strong gravity is. Because the mass is
You
a
have
variable.
to see it across all the sizes.
Right. Yeah.
Okay.
Yes. So he says if we try to get something that nature produces, her own pure number that has nothing to do with inches or years or anything to do with our own dimensions.
Wow.
We can do it this way. If we take a fundamental particle, such as an electron, any different one will give a different number. But to give an idea, let's say 2 electrons are 2 fundamental particles, and they repel each other inversely as the square of the distance due to electricity. And they attract each other inversely as the square of the distance due to gravitation.
Right. So so now you've got a fundamental thing. It's all this. You're using it for both to test both.
Yeah. This is making a bit of an assumption that every electron is the same.
Right.
But what he's basically saying is...
okay, that has been checked time and time again, and he does point this out later in the book that, like, you can't check every electron.
No, you can't.
So you can check enough to where you can be confident that, like, okay,
they're pretty close.
The That's right.
That's what I'm saying.
And you have to do this, otherwise you will never make any progress.
That's right. Yeah. All of this is about recognizing a pattern in slightly noisy data.
That's
or
right.
Or sometimes extremely noisy data.
And also always having an amount of uncertainty.
Yeah, that's right.
And being able to live with that.
Right. So given the idea that we say that any 2 electrons are basically going to be extremely close to being the same thing in terms of how much mass they have and how much electrical charge they have. Okay, so we're using the electron as the 1 in this circumstance here. That they repel each other inversely as the square of the distance due to electricity, and they attract each other inversely as the square of the distance due to gravitation. Then you can check the ratio of the strength of those 2 forces to each other using that. the electron being your fundamental thing here. So he says the ratio is illustrated in Figure 7. And in Figure 7, he shows gravitational attraction over electrical repulsion equals 1 over 4.17 times 10 to the 42nd power. In other words, gravity is 1 in this formula here. And if gravity is 1, then the strength of the electrical force is 417 and then 42 zeros. Or whatever. Or
there's 42 digits total.
Yeah, 417 and then 39 zeros.
Yeah.
That's what it is.
42 digits.
Yeah. So that's a huge difference in strength.
Yeah.
So he says the ratio of the gravitational attraction to electrical repulsion is given by a number with 42 digits tailing off. So therein lies a very deep mystery. Where could such a tremendous number come from? I find it interesting that he states it that way.
That it's a tremendous number.
No, that where does it come from?
Oh, where does it come from? Okay. I don't know.
That to me, yeah.
I think of it as like, I don't think of it as a number, I guess. I think of it as just, I guess, a ratio or so. I don't know.
Yeah, it is. But it's the come from that is really what he's getting at here.
Yes. Yes, you're right.
Because what he's asking, and he will go on to see this, but what he's asking is, does this number exist anywhere else?
Right.
Because we're already why are we doing this? Because we're
looking
same
for patterns.
Well, we see the same relationship, this inverse square.
Yeah.
So now we're saying, well, okay, when we check these two against each other, we get this enormous number. Does it also come from somewhere else in the system? Right? So he says, if you ever had a theory from which both of these things are to come, in other words, both the inverse square and this gigantic number, how could they come in such disproportion? What equation has a solution which has for two kinds of forces an attraction and a repulsion with that fantastic ratio? People have looked for such a large ratio in other places. They hope, for example, that there is another very large number. And if you want a large number, why not take the diameter of the universe to the diameter of a proton? Amazingly enough, it is also a number with 42 digits. And so an interesting proposal is made that this ratio is the same as the ratio of the size of the universe to the diameter of a proton. In other words, the ratio of the strength of gravity versus the electrical force is the same as the diameter of the universe to the diameter of a proton.
That is insane to me. That is freaking insane. But to me, that's another way to illustrate how vastly different.
Yeah. These two forces are.
That's a wonderful illustration to show you the difference.
But I also agree with him that there's this haunting possibility that that they are arising from some more fundamental thing. Okay.
Yes, I love that.
He's a little bit skeptical about this particular comparison.
Yeah, of course.
But at the same time, he's saying, like, you can understand why people are looking for this. And the whole thing about where does this number come from is they're like, well, does it exist? Does it some similar number, an enormous number, exist somewhere else? Can we find it? And they find it in this. Well, they don't find it.
It's a close approximation.
Yeah. It has 42 digits.
It's got 42 digits,
which means, like, in terms of being closeness, it's probably the same. Like it would be. Like, even if one of these is like 417 and then a bunch of zeros, if the other one's 985 and a bunch of zeros, it's close enough, just like all the rest of these measurements, right? But he says,
and that, well,
the universe is expanding with time. And this means that the gravitational constant would be changing with time as well.
If it was connected directly. If they're
connected directly to, in other words, if this giant number between the two strength of the forces is connected to the
size of the universe.
Unless the protons are also getting bigger.
They might be getting bigger, and we
would never know.
No, because everything would be getting bigger with it.
So would we in all of our instruments.
That's right.
God. So they could be connected. So he says, that would mean the gravitational constant is changing with time, and although that is a possibility, there is no evidence to indicate that it is a fact. there are several partial indications that the gravitational constant has not changed in that way, so this tremendous number remains a mystery. Finally, he says, in connection with the laws of physics on a small scale, we have found that the behavior of matter on a small scale obeys laws very different from things on a large scale. So the question is, how does gravity look on a small scale? Well, this is called the quantum theory of gravity, and there is no quantum theory of gravity. People have not succeeded completely in making a theory which is consistent with the uncertainty principles and the quantum mechanical principles. And I think that's still true.
Yes, I think so. They're still working on it.
Yeah. So you will say to me, yes, you told us what happens, but what is gravity? Where does it come from? What is it? Do you mean to tell me that a planet looks at the sun, sees how far away it is, calculates the inverse square of the distance, and then decides to move in accordance with that law? In other words, although I have stated the mathematical law, I have given no clue about the mechanism. I will discuss the possibility of doing this in the next lecture, which is called the relationship or the relation of mathematics to physics. But in this lecture, I would like to emphasize, just at the end here, some characteristics that gravity has in common with the other laws that we mentioned as we passed along. First, it is mathematical in its expression. The others are that way too. Second, it is not exact. Einstein had to modify it, and we know it is not quite right yet because we have still to put the quantum theory in. That is the same with all our other laws. They are not exact. There is always an edge of mystery, always a place where we have some fiddling around to do yet. This may or may not be a property of nature, but it is certainly common to all the laws as we know them today. It may only be a lack of knowledge. I love that he implies that this may be a property of nature.
That's great. This is why I love this guy so much. You know.
He's like, because the common things you would see here is, well, we just got to do some fiddling. It's only a lack of knowledge or being able to measure or whatever. But
Right.
he implies maybe that there's some deeper thing happening here.
Right.
But the most impressive fact, he says, is that gravity is simple. It is simple to state the principles completely and not have left any vagueness for anybody to change the ideas of the law. It is simple, and therefore it is beautiful. It is simple in its pattern. I do not mean it is simple in its action. The motions of the various planets and the perturbations of one on the other can be quite complicated to work out, and to follow how all those stars in that globular cluster move is quite beyond our ability. Yes, like just 3 of them is beyond our ability to predict.
Right.
The 3-body problem. It is complicated then in its actions, but the basic pattern or the system beneath the whole thing is simple. This is common to all our laws. They turn out to be simple things, although complex in their actual actions. And finally comes the universality of the gravitational law, and the fact that it extends over such enormous distances that Newton, in his mind, worrying about the solar system, was able to predict what would happen in an experiment of Cavendish, where Cavendish's little model of the solar system, 2 balls attracting, has to be expanded 10 million times to become the solar system, and then 10 million times larger again we find galaxies attracting each other by exactly the same law. Nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry.
Love it.
Yes.
God, it's so good.
Yeah.
It's just amazing. I love it. Only the longest thread.
Yeah, that's a great way to put that. That the fact that, you know, that the idea that you can see this law working in these tiny, well, you know, a couple of giant lead balls or whatever is tiny relative to the size of the universe, but you can see the same law, inverse, you know, relation acting on them, as you can see when you look at giant galaxy clusters, and that tells you that the thread is long.
Right.
In terms of distance, like the length of the thread is distance and size, right? It just doesn't matter, you know.
Right.
And I think, as far as I know, that, you know, like Feynman was saying that even in this giant galaxy cluster, this was the largest structure in which we've seen this working well today. They're much larger structures we see this working.
Right.
But it's interesting because now you can kind of see how the confidence in these relationships, these laws of how things work together, results in things like people talking about dark matter. In other words, dark matter is a term that is like thrown around all the time, but really what it is a bunch of observations
that don't match
the predictions of the calculations based on the laws.
So they name it something, thinking that they've found this is the confidence in the law resulting in what they think is the discovery of a new phenomenon.
Right.
As opposed to the law needs to be corrected.
Right. So the answer to the question...
And there are two camps.
Yeah.
Right. But the law needs to be corrected camp is dwindling.
Yeah.
Because they've also found in the cosmic microwave background and all that kind of stuff.
Yeah.
So the indications are that there is some new phenomenon. But
yeah. There is a phenomenon taking place. The question is does the law need to be corrected, or is this just another phenomena that has nothing to do with gravity? It's just affecting the... You know what I'm saying?
Right.
Like, is it not? Because that's the thing about dark matter, is that the assumption there is that it's more gravity.
It's more stuff that has that mass. And therefore there's more of a force.
Right.
Acting upon everything there.
Yeah. And it's just called dark because we can't find it or can't see it.
Yes.
So that's what I'm saying. Like, I wouldn't fall into the camp of like the law needs to be fixed. But I would say that the whole thing with Jupiter's moons, that's more like what I think is happening.
Yes. In other words, this is why we go back to the question of, does gravity arise from mass? Is it a force that's directly correlated to mass?
Yeah, that's one question. Yeah, and Feynman is showing you why they're really confident in saying that. You know, that, like, in other words, that whether mass is generating gravity or not, it's always correlated with gravity.
Yes.
At least as far as we know.
So can there be a force of gravity that is not directly correlated with mass, with matter?
Yeah.
With mass.
Right.
Or
that would make it maybe a gravitation-like force, but not necessarily gravity itself, right?
Yeah, I don't know.
Yeah. I'm just saying that there's this. It just shows you what possibilities are. Like, you could look for, like you were saying, you could look for changing the law. Well, that's most people are less and less inclined to think that that's what has to happen. Other people are like, well, there's a bunch of gravity out there, and the gravity must be connected to material somewhere, because we always see gravity as correlated with material. Whether they think that mass is generating the gravity or not doesn't matter in that instance. They're just looking for mass.
Right.
But the question is could it be more like what was happening with Jupiter's moons? There's no mass involved with that.
Right.
That was about the speed of light.
That's right.
That's what I mean.
In other words, there wasn't something slowing down the moon and then speeding it up.
In other words, like the whole Jupiter system was getting closer and farther away from a bunch of dark matter. It had to do with the speed of light. The gravity didn't even apply to how they fixed that problem.
That's right. Yes.
So that's what I'm wondering is, like, yes, the question is could there be a source of a gravitational like pull that has that isn't correlated to matter, or is it just something completely different?
Right. Yeah, I know what you're getting at.
And then
that's a really good point.
Yeah, and then the other thing is that we have also the what's the other one? Dark energy.
Right.
The thing that's pushing everything away from everything else.
Is that somehow correlated to the electrical force?
Yes. Is it correlated to the electrical force? Does this imply that? Is it connected to dark matter somehow? Is it a polarized force?
Protons are getting bigger, folks.
That solves all the problems. And why is it a proton and not an electron? Like, why? Is it that you get close to the same number if it's a proton? But why did they particularly choose that one? Why not a neutron, or why a proton, not an electron?
He doesn't say. I don't know.
I don't know either. I think it's just like that's the one where it's close.
That's the closest one. Yeah.
But if it's true that that's the closest one, does it imply that the proton can give us a clue as to why this relationship exists? In other words, the properties of the proton might give you a clue.
Yeah, that would be cool.
Because it is the proton, not the electron or the neutron.
Mm-hmm.
It has a positive charge, not a negative charge, and it's not neutral.
Right.
I don't know. Like, these are the things that happen in my brain when I'm reading through it. I'm like, why is it the proton? On all the other ones, you were choosing the electron as the fundamental, you know, and suddenly you're giving me a proton now. It's way bigger than an electron. I don't know.
Yep.
It's fun stuff.
I totally agree. I love it.
All right.
That was great, man. Perfect timing. First lecture done.
Yeah. And maybe we can try tackling some more. I don't know how much of the next lecture, the relation of mathematics to physics, has some great stuff in it, but I don't think we need to go through nearly as much of it as we did in this first one.
The first lecture, really, you have to go through it in detail because it lays out the process of this is, and as he says in the beginning, like, you can use this example over and over in your mind to see, like, this is how the process is happening throughout all of these discoveries and the connections between these laws.
Yeah. Yeah. So I'm just thinking, like, you know, we may not, we probably won't do a show per lecture, but maybe we can tackle several of the contents from several of the lectures in the next episode, because I do want to go through some of the stuff in lecture 2, the relation of mathematics to physics. There's some great stuff in there, but maybe that show will be 3 or 4 of the lectures.
Cool. Sounds great.
And we'll see, you know, maybe.
Well, this has been a long time
we've been talking
dream
about this for
of
a long
mine
time.
to do this book, so I'm very happy with this, and it's going great. I love it. So,
all right, guys, you can get a hold of us, Brothers of the Serpent, at gmail.com. Check out the website, brothersoftheserpent.com. That's got all the podcast-related stuff there, including our merchandise and how to support the show to join the Pyramid Scheme with Patreon or PayPal. If you join the Patreon, there is extra content, Patreon-only content there. You can also join the Discord if you want to talk to a bunch of other snakes. There's a lot of people in there, always having conversations about cool stuff and discussing the shows and topics that are not discussed on the shows. And, I think that's it. Thank you guys so much. We love you guys.
always have.
Always will.
Good night, Atamu.
Get back to work.
So what the angels have to do is to beat their wings in toward the sun all the time. That the motion to keep it going in a straight line has no known reason. The reason why things coast forever has never been found out. The law of inertia is no known origin.